On March 26, 2010, an irreversible threshold was crossed in the dark waters of the Yellow Sea. The Republic of Korea ship Cheonan, a fully operational surface combatant, ceased to exist as a single coherent vessel. In a fraction of a second, the warship was severed in two. 104 personnel were aboard when the structural integrity of the hull catastrophically failed. 58 survived. 46 sailors were killed in the disaster as the separated hull sections flooded and disappeared beneath the waves. This was not a gradual foundering or a slow taking on of water. This was the sudden, violent destruction of a major naval asset. The Cheonan was a Pohang-class patrol combat corvette, a formidable platform engineered for the unforgiving environment of coastal naval warfare. She was a 1,200-ton class ship of hardened steel, heavy machinery, sensors, and armament. From the leading edge of the bow to the stern, the hull stretched nearly 290 feet. Built for coastal defense and security patrols, the ship carried weapons and equipment for anti-surface, anti-air, and anti-submarine missions. Surviving in the contested maritime environment near the northern limit line required a vessel capable of operating under pressure and maintaining mission capability. The corvette was designed to fight in that pressure, carrying sonar, torpedoes, and depth charges as part of its defensive profile. The sequence of destruction was attributed by the official investigation to a heavyweight torpedo identified as the CHT-02D. This weapon was reported to use acoustic and wake homing with passive acoustic tracking. It was not a random explosive drifting in the sea, and it was not a simple, unguided projectile. It was a naval weapon designed to approach a moving target through the underwater environment. As the Cheonan moved on patrol, her machinery, propellers, and moving hull created sound and disturbance in the water. The official record does not publicly reconstruct every second of the torpedo's approach, but it identifies the weapon as a homing torpedo capable of delivering a non-contact underwater blast near the gas turbine room. Below and to port of the hull, the detonation geometry allowed the surrounding water to carry the explosive load into the ship's backbone. The keel snapped instantly. The hull severed completely along the midsection, right through the heavy gas turbine room, dividing the unified vessel into two distinct, unsupported structures. The stern section, which housed the heavy propulsion machinery and the main drive shafts, was suddenly cut away from the buoyant forward compartments. At the exposed brake plane, it lost watertight integrity, flooded almost instantly, and dropped directly to the seabed. The bow section, violently detached from its rear driving force, pitched erratically in the water. It drifted forward purely on its own lingering momentum. Water poured unhindered into the massive, open tear where the center of the ship used to be. Slowly, the forward half lost its remaining reserve buoyancy and slipped beneath the surface, following the stern into the dark. Two jagged wreckage fields now rested entirely separate in the cold ocean depth. The corvette had been completely eradicated from the surface, yet the true engineering paradox remained hidden below. The warship had been torn apart with sheer catastrophic violence, severing heavily armored steel and thick structural frames, but the weapon itself had never actually touched the hull. The exact mechanism capable of ripping thousands of tons of military steel in half without physical contact remained completely unseen. A detonation of roughly 550 pounds of high explosive violently transformed the water column about 10 feet off the port side. The official investigation placed the blast at a depth of about 6 to 9 meters, or roughly 20 to 30 feet, positioned to port of the gas turbine room. This standoff zone set up the shock and bubble sequence that followed. When the massive explosive charge detonated, the chemical reaction instantaneously converted the solid material into a rapidly expanding sphere of superheated gas. The immediate physical consequence was a primary, high-velocity shockwave radiating outward in all directions. Traveling at supersonic speeds through the dense aquatic medium, this initial acoustic pulse violently slammed against the underwater plating of the hull. It delivered a massive, blunt force concussion across the entire lower structure of the vessel. The shockwave aggressively rattled the heavily compartmentalized ship, but this extreme acoustic blow was only the precursor to the true destructive mechanism. Behind the leading edge of the shockwave, the detonation created a rapidly expanding gas bubble in the water column. As that bubble grew beneath the target, it displaced the surrounding sea and drove a powerful upward load into the lower hull. The midsection was forced upward while the bow and stern resisted that motion through their own mass and inertia. For the steel structure, this meant brutal bending stress, the center being driven one way, the ends pulling another. Then the bubble lost pressure and began to collapse under the weight of the surrounding sea. In a non-contact underwater explosion, that collapse can create complex water motion beneath the hull, including a concentrated upward jet and a sudden change in support under the ship's middle. It is the combined work of shock pressure, bubble expansion, collapse, bending, and localized hydraulic impact. That combined loading overwhelmed the damaged structure near the gas turbine room. The official investigation linked the fracture pattern to shockwave and bubble effects, with upward deformation of the center vertical keel, steep bending of shell plating, and localized punching shear damage in vulnerable lower hull areas. The continuous strength of the hull failed and the Cheonan split apart. But models, simulations, and damage theory were not the same as untouched forensic proof in a high-stakes international inquiry. The physical truth still had to be read from the torn steel itself. Isolating that structural evidence required recovering the shattered hull sections without distorting the damaged metal geometry. The shattered remains of the heavy warship were pinned under 154 feet of dark, violently moving water. The seabed of the Yellow Sea presented a brutal geometry problem. Massive tidal forces squeezed high volumes of water through the regional topography, generating continuous crosscurrents moving at 3 to 5 knots. Operating at this specific depth in such an aggressive fluid flow meant near zero visibility and extreme hydrodynamic pressure against any human attempting to access the wreck. The sheer force of a steady 5-knot current strips body heat rapidly, rips at surface umbilical hoses, and makes precise manual labor nearly impossible. Yet, under these severe operational limits, specialized naval divers had to route heavy salvage chains entirely underneath the jagged, highly unstable steel structures resting in the sediment. The engineering imperative was not simply to drag the heavy hull sections back to the surface. The operation had two urgent demands at once: recover the dead and the ship, while treating every lift as an investigative act. Standard heavy salvage focuses on breaking bottom suction, securing lift, and moving weight. Here, the consequences extended into the evidence itself. The shape of the torn exterior plates, the angle of internal frames, and the condition of the fractured steel at the open midsection were critical clues for reconstructing the direction and nature of the destructive force. The severed brake plane was highly compromised. The violent detachment had left the ends of both the separated bow and the stern wildly distorted, lacking any of their original continuous structural reinforcement. The longitudinal strength was completely gone. If the divers placed the heavy lifting chains incorrectly, the sheer upward force applied by the crane would squeeze the weakened hull. The massive dead weight of the waterlogged steel resting on the chains would cause the remaining transverse bulkheads to buckle inward. Any new bending, crushing, or warping introduced by the salvage chains would permanently contaminate the physical geometry of the brake plane. The required metallurgical proof would be completely destroyed by the rescue effort itself. To reduce that risk, the dive and salvage teams had to rig the separated hull sections with extreme caution. Public reporting confirms that heavy chains were connected around the stern and bow for crane lifting, with the stern requiring 3 chains and the bow planned for 4. Each connection mattered because the chain count and contact points would determine how the crane load entered the broken hull. For days, the teams fought weather, currents, poor visibility, and the sheer mass of the ship sections. The goal was to spread the lifting load across stronger remaining structure while avoiding unnecessary crushing or tearing at the exposed brake. Once the chains were secured and the crane was positioned, the operation moved from underwater rigging to the even more dangerous moment of lifting a flooded warship section back into air. Securing the chains completed only the underwater phase. The next crisis would begin when the flooded steel was pulled free of the seabed and forced toward open air. On April 15, 2010, floating cranes began raising the severed stern section, applying enormous vertical force to wreckage that was both heavy steel and flooded internally. As the stern came up, the load changed. Water trapped inside the compartments became dead weight, and the severed hull no longer had its original continuous structure to distribute that weight cleanly. Public accounts from the operation described the stern as weighing hundreds of tons more because of the water inside, so the lift had to proceed slowly enough for crews to control weight, drainage, and placement. Once the stern was drained and secured on a transport barge for movement and examination, the same sequence followed for the bow. On April 24, 2010, it was raised by large floating crane, drained, and placed on a barge. The process was careful not because the wreck was stable, but because every movement risked adding new damage to metal that investigators still needed to examine. With both sections secured in open air, the operational phase gave way to forensic examination. The geometry of the torn steel, the curvature of the internal frames, and the condition of the fractured plating could now be inspected in detail. The recovered metal presented a severe physical contradiction for the investigators. A surface collision and an internal explosion would each leave different signatures, but the break area pointed in another direction. The bottoms of the bow and stern sections near the failure point were bent upward, and the center vertical keel showed significant upward deformation. To interpret that distortion, salvage engineers and forensic specialists used three-dimensional laser scanning and structural analysis across the open, jagged wounds of both sections. The digital mapping helped record the vector of sheared beams, warped plating, and damaged bulkheads. The pattern described by the official investigation showed shockwave and bubble effects on the lower hull, upward bending at the failure point, and no clear indication that a torpedo casing had scraped or torn directly through the ship. Together, those findings supported the conclusion that the destructive force came from a non-contact underwater explosion below and to port of the gas turbine room. The microscopic state of the torn steel added another layer to the analysis. Metallurgical experts examined the points where metal plates and structural members had failed. The official report described punching shear damage in vulnerable lower hull areas, especially around the bottom plating near the gas turbine room. That kind of damage fit the broader shockwave and bubble effect scenario, a sudden, concentrated load acting upward through the hull, not a long scraping strike from a solid object. The steel did not need to be sliced by a literal blade of water. It needed only to be overloaded faster than the damaged structure could absorb. The physical geometry of the steel formed the primary forensic pillar, but the chemical evidence added another crucial strand. Forensic teams sampled the hull, fracture surfaces, seabed material, and recovered torpedo components. The official laboratory work reported traces of explosive compounds, including HMX, RDX, and TNT at multiple locations. It also reported adhered white material whose composition was compared between the hull and the torpedo propulsion section. Those findings were important, but they should not be collapsed into a single simple substance. The white adhered material and the explosive residues were related lines of evidence, not the same thing. Taken with the deformation of the hull and the recovered torpedo parts, the chemical findings strengthened the official conclusion that an underwater torpedo explosion had initiated the destruction sequence. Taken together, the map deformation, fracture evidence, and chemical findings gave investigators a coherent physical case for an underwater torpedo explosion. Yet that case still lacked the hardware that had delivered the explosive payload. The massive detonation had instantly vaporized the forward warhead section, but the heavy rear propulsion unit should have survived the blast. However, its exact location within the dark, tidal-swept wreckage field was a complete unknown. Finding a shattered, disconnected piece of military machinery scattered somewhere across a vast expanse of ocean floor presented a severe procedural challenge. Returning to the waters around the incident site, specialized teams shifted from heavy hull salvage to a targeted seabed search, using special nets in areas assessed as most likely to contain debris rather than treating the entire bottom as a blind industrial dredging field. Surface crews worked a controlled search area, hauling up seabed material and sorting it for dense, machined metal that did not belong to the anatomy of the sunken corvette. It was evidence recovery as much as extraction, and the method had to balance speed against the risk of damaging what it was trying to find. The marine environment fought the extraction effort, and every hull could contain irrelevant debris, rocks, and ordinary scrap. But the controlled search finally produced the critical hardware investigators had been looking for. On May 15, 2010, teams recovered parts of a torpedo propulsion section, a propulsion motor, contra-rotating propellers, and steering components. These components were not part of the Cheonan's gas turbine room or severed ship machinery, so investigators compared their size, shape, and design to the schematics of a North Korean CHT-02D torpedo, described in export material. The official investigation also cited a Korean marking inside the rear propulsion section as consistent with a previously obtained North Korean torpedo. The physical recovery of these propulsion components became the final major link in the official investigation's chain of evidence, giving investigators a candidate delivery system that fit the blast profile and the damaged geometry. The delayed forensic salvage operation became more than hazard clearance or vessel recovery. It turned loss, wreckage, and scattered debris into usable evidence. In official terms, investigators concluded that the Cheonan had been split and sunk by shockwave and bubble effects from an underwater torpedo explosion, with the weapon identified as a North Korean CHT-02D. The salvage record left that conclusion in physical form, open to examination, challenge, and weight.